Hello, everybody. Hopefully, you have your feet wet a little bit with proof and kind of the idea that you start somewhere and you end up somewhere, and you got to believe in what you're saying. Experience is your best teacher with proof, so I hope a whole day has changed your life. All right, we're going to start out with this thing called mathematical induction. This is it's just so powerful and so beautiful what how they came up with this, but it takes a little bit to believe in. Like you're going to go through the ropes with me. You're going to do the steps I asked you to do, but you got to step back sometime and just make it work. All right, this is in the higher level syllabus. Um, Proofs should be incorporated through the course where appropriate. So this is not like a standalone problem. It's kind of like part of a bigger problem. And we will use it to mess around with complex numbers. We'll mess around with differentiation, the sums of sequences, and divisibility. I feel like Alex Trebek, God rest his soul, um, when he's talking about the different categories. And so we'll do that and honor him. All right, so a couple of quick examples. Can I get them all in there? I'll try. So complex numbers. We know that we can write a complex number as a plus bi. We know we can take that to a power. What you don't know is I can change a plus bi to be a different form. I can take that to the same power. And then using proof by induction, I can show that when I take this to the higher power, it really gives us this result called de Moivre's theorem. Amazing. You're going to love it. It's going to change your world about the number one and roots and multiplying with regular polygons. What? That just all is together. Incredible. All right, differentiation. So, man, last year you learned how to differentiate, but why stop with one, two, three? Why don't you do it n times? So we might get a formula or a function and then want to know what the nth derivative looks like. And there is a way to show you that it will always be in this form. Come on, really? Yeah, really. Sums. This is going to be a big one. We're going to do these two together, the sums and divisibility. In other words, if you're given a term and we have a function, a formula for the first term, the second term, the third term, whatever, then if I add all those terms up, can I get a formula? So in this case, if I plug in 1, I get 1 over 1, 1 half. And then I plug in a 2, I get 1 over 1 sixth. So if I add all those up, I claim that the sum will be in this form. Interesting. All right, so now finally in divisibility, we have a beautiful statement. All of the terms will look like this. So I plug in a 3, that term is 4 to the third plus 5. I plug in a 4, so forth and so on. But I'm going to claim that using proof by mathematical induction, I can prove that all numbers, all terms of that sequence will be divisible by 3. So today, I want you to be able to attack problems of divisibility and summation. What? Yes, Devil's Tower. So it is amazingly, it's a geology just crazy. Now you can fast forward through all this if you want, but has a connection to proof by induction. So when I first started teaching, I ran into some yahoos that actually were very positive, and they taught me how to climb. So we climbed little things around Horsetooth and got better and better and better. And then it culminated at this climb called El Matador. El Matador. This was very scary. Not like mathematical induction. That's not scary. But the geology and the volcanoes, and ask your teacher about that. These pillars. Well, these right here, it's just world famous crack climbing. And it's just, if you're a rock climber, you understand that you don't run into this very often because it's not very sustained. These things start at the bottom, they go all the way to the top, and if you know the moves, you can do it. Um, I don't know that person. Let's go. Yeah. So this is El Matador, and man, it is just really scary. Let's see. Oh yeah. So you're stemming right here. Um, and you're putting in places of protection. So if you fall, cool math problem, if you fall from here, you fall all the way down here. So twice the distance, huh? You hope. All right, so I did not lead, thank goodness. I basically got pulled up this thing. But while I was climbing, I made this idea that it's kind of like proof by induction. Now, why is that? Well, to do this move, you got to get your hands in the crack, and it's notice the thumbs are down, really important. So you got your hands in there. The feet gets wedged in there, and if you can get into that position, then all you have to do is repeat and repeat. So you do this, move your hands up, move your feet up, do this, move your hands up, move it. So this like domino effect happens. Once you're here, then do 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 do, boom, you're at the top. But most importantly is can you start? So that brings us to the 2 steps of mathematical induction. Please write this down. Please have this. If you cannot do this proof, then, and we'll come back to the Devil's Tower analogy in a second, but if you cannot do this, the proof in itself, you get a lot of points by knowing that there are 2 steps. I call this the base case. And notice n is greater than or equal to a. It's basically saying, hey, is our proposition at the very beginning, is it even true? In other words, can we even get onto Devil's Tower? Like, can we even get into that starting position? Because if we can't even start, then why even see if we can climb it, right? So then this second step is really cool, really cool. We assume this is true. We assume we can make it up so far. Now we have to prove, no matter where we are, can we go to the next step? All right, so notice the k and the k plus 1. So the kth proposition is somewhere up there. And can I prove that if I make it that far, I can make it to the k plus first one? That little jump that connects those 2 dominoes, very important, very important. In fact, speaking of dominoes, I have an amazing video for you. Here it is. Daha, maybe we should start this at the beginning. Get back there. So that means we can start, and then if somehow we've proven, and then all of a sudden we can climb all the way up. I know, it doesn't make sense to you yet. Yet. Critical. How do you make this go away? All right. Oh, now I've made everything go away. All right. So it's a remarkable thing to think about is that the first thing you have to do is prove that you can start. So the first thing is the base case. And notice there's nothing I can say because the things that we're going to use to prove are all those 4 are totally different ideas. So I can't say this is how you show the base case. You just look at the first proposition. And then the second thing is assume this proposition at the kth step is true and show p sub k plus 1 must be true. A way to write this mathematically is, which I like, is p sub k implies p sub k plus 1. Okay. What in the world? Let's try a few problems. So divisibility, given a general term, show that it will always be divisible by a certain number. So just to be clear, how would we show something is divisible by m? Well then, all we have to do is show that we can rewrite that number as m times an integer. All right, so our goal will be, if it's divisible by 3, can I rewrite this so it's 3 times something that must be an integer? Let's try it. All right, so a sub n equals 4 to the n plus 5. We're going to show that this is divisible by 3. Upside down a, n, weird e looking thing, z plus. So you're going to have to understand notation. That is for all positive integral values of n. So z plus is 1, 2, 3, 4, 5, 6 on up forever. N is an element of that. There you go. So let's start. There's 2 steps in proving this. One, the base case. So the base case in this case is 1. So we're going to plug in 1. So if we plug in 1, oh, sorry, the question I asked myself, you don't write this down, but if you're not asking yourself what's going on, is the first term divisible by 3? Because if it isn't, why would I check to see if any of them else were, if the first one's not? So we just plug in a 1, we get 9, and we say yes. Now, if you want to be clear, maybe you write this as 3 times 3. So you're really showing that it's 3 times an integer, but don't. 9 is divisible by 3. You're smart. You can handle it. All right. So P1 is true. The base case is true. We love that. Life is good. All right. Step 2. You actually write this. This is a really important step to write in the proof. Okay. So you assume P sub k is true, or you say P sub n is true when n equals k. So I'll write that on the next one. All right, that is what we want to show is, or what we want to assume is, if I plug any number I want, like 238, I'm going to assume that's true. No big deal. Now what I want to show then is the next term divisible by 3? If I know this term is divisible by 3, can I somehow show that the next term is divisible by 3? All right, so let's see if we can. All right, so what do we know? We know that the kth term is divisible by 3. That means it can be rewritten as 3m. Divisible by 5, I'd write 5m. Divisible by 17, I'd write 17m. It's kind of nice to tell the world that m's an integer. You can write it out in words, or you can say it in this fancy notation. All right, so let's kind of now mess around. What is the k plus first term? Well, I just plug in k plus 1 in for n, and I get this. Now I'm looking at this and I'm wondering, hey, I know this is true, but how does that help me with this? I don't know if it does. So I'm showing you this for a reason, because they all start to look the same as soon as we do 5 or 6 of them. This is a key step, is understanding that's 4 to the k times 4 to the 1. I don't know, I have this variable, so I like to put the number out front. Now, we know this is true. This is our assumption, okay? So now we can solve for 4 to the k because I see a 4 to the k. And this is going to be a huge part. This is how you use your assumption in the kind of, as you manipulate to try to get somewhere where we know is true. So that now is 3m minus 5. Plug it in. And remember, our goal is to show that a sub k plus 1 is equal to 3 times something. Multiply it out, add, factor. Have we gotten to the stage of 3 times something is that something? We've done it. Well done. Proud of you. So we need to write this. Okay, this can be part of the points. If you don't, it's called a remark point, because it's remarkable. You knew I was going to say that. All right, since P sub 1 is true, the base case is true, you can say all that. And P sub k implies P sub k plus 1. In other words, and since P sub k plus 1 is true when P sub k is true, that means the same thing. P sub n, now, I use P sub n, is true for all n. That's pretty powerful. All right, let's try another one. All right. I don't know if we're going to have time for this. Let's just do if you want to check it out, you can check out the notes. We know this is really cool. they use 5 plus 1 to the n to kind of represent that. Use the binomial to show that you'll always have a 5 in there, so you can factor it out. So that's kind of cool. Um, I don't know, it's kind of cool. Let's look at the principle of mathematical induction. All right, base case. Really important, n equals 0 here, not 1. Why? Because this thing is supposed to be good for n is greater than or equal to 0. So we use our lowest value of n, plug it in, 1 minus 1 is 0. Is 0 divisible by 5? So that's another reason I picked this. Yes, it feels weird, but the remainder is 0. 5 goes into it 0 times with remainder 0. If it has remainder 0, it is determined that it is good to go. All right, so base case is now done. Now we need to assume the kth statement is true, and that is the kth term, a sub k, which is 6k minus 1, is equal to 5m, is divisible by 5. That's what we know. All right, now divisibility is, now we just look at the k plus first term. What does it look like? Well, the k plus first term is this. Now, you're going to see in my notes, I'd like to put the WTS, and that's basically want to show. That's what I want to get to. It's not something part of the proof. I think it's important to kind of know where you're going or what you want to get to, and as you learn proof, I think it's really important. So go ahead and do that. I don't think you'd be counted off with want to show, and I just think it's important. Oh boy. Oh boy. Oh boy. All right. Just gentle. Okay. Let's just show you all those steps. All right. So we know that if I remember the same thing happened, we separate those. That's 6 to the first. That's the same thing that we just did. We make our substitution from the assumption. So now anytime I see a 6 to the k, I can put a 5m plus 1. I do it, multiply by 6. I get 30m plus 5, which is factorable by 5, which means a sub k plus 1 is divisible by 5. Okay, life is so good. We're so set that we want to state our final statement. Since the base case is true and p sub k implies p sub k plus 1, then we know it's true for every single one of these. Do they get a little dicey? Absolutely. Are you scared? You should be. This is a hard problem. I did it much differently than the book. So, you know what you should do is just look at the solutions on mine and the book and see. I think mine are much more likely to happen. I think their algebra is way cooler than mine, but I don't have that in me. So we'll just go through it real quick. We want to show that for every n value I plug in, it'll be divisible by 13 or 17. Plug in 1. You're going to show it works. Great. All right. We're going to assume this is true. We're going to assume the kth term is equal to 17 times an integer. What I want to show is somehow when I plug in k plus 1, work it out so I get 17 times an integer. Whew. All right, so this is a sub k plus 1. I plugged in k plus 1. That's looking a little gross. So maybe I clean it up. Okay, and I'm reminding myself I know this. I've got this in the bag. I've got this. I can use this as a substitution. I just need to find this somehow. Oh my goodness. Well, my idea is, can I somehow get this term by itself? If I can, then I can substitute what it equals. I could subtract that 2 to the 3k plus 1. I just picked a term and I'm going to solve for it. So I notice that I've got this 2k plus 1, but I've got this plus 2 here. Got this plus 2. But that is, see how working exponents, this is why we do that. That's why we call it pre-calculus. So we feel fundamentally good with working with exponents. We can manipulate, we can do what we want. Um, so I see that I have my 3 times 5 to the 2k plus 1. Pull out the 25, and there it is. Whatever happens, happens over here. I pulled the 2 to the third out, then I put it back in. I didn't know what to do. I was scared. I make my substitution. Okay, at this point in the game, I have no idea if I'm right or wrong when I did this problem. Okay, it doesn't look good. I'm like nervous, but I plug it in and then I kind of multiply some things out. Um, I don't multiply. I know this is 25 times 17 times m. That's divisible by 17. I love it. Then I get this gross stuff I don't even know what to do with. And then I've got this. Now I notice here that these exponents are the same. Okay, why? Because when I went from here to here, as I was writing this, I'm like, hey, 3k plus 1. Oh, I can just pull out that 2 to the third and get the 3k plus 1. Why is that important? It's basically common like terms. I have 25 of these here, and I have 8 of these here. So 25, negative 25, plus 8 is negative 17. Oh, come on. I've got a 17 in both terms. Factor it out. Babamskis. Oh, if you know the process and they give you a problem, it's probably going to work out. So you just got to believe. Whew. All right, I'm going to stop. No, I'm not. I'm not. I'm going to show you the way. Do I have one more? Oh, these are good. Yeah, you'll like those. All right, I'm going to stop there for divisibility.